How did the assignment go?
Mostly good. So a new one is posted. And this one is a good bit longer, at least in terms of the number of problems. I'll let you tell me about the number of hours that it takes to complete, but we've covered quite a bit, are on pace to cover quite a bit, so it makes sense for all of this level of practice ahead of the next exam. I think I said this yesterday, but I anticipate about 90% of the overall population who would be in this class to require help at some point going through, especially some of these pumping lemma proofs. So let me know how I can be useful to you. There is no shame in that whatsoever. I see that as engagement and learning. And I still don't think I've seen any of you in office hours, which is surprising given the last time that I taught this course, half the class followed me to office hours on a nearly daily basis. All right, so we moved on from the pumping lemma and we were able to show that certain languages aren't regular. So we're gonna look at the next class of language that is the context-free language. As part of that proving that a language wasn't regular, we looked at this language A to the N, B to the N. We saw that we could replace the A's from this and B's with open and closed curly braces. This allows us to look at nested control structures and allows us to kind of do that. And then we need some kind of more complicated grammar and state machine rules. We want to be able to reason about things like nested control structures. And we will find that a significant number of features of programming languages can actually be modeled by context-free languages. So they're worth studying. They are the most studied individual class of language because they have the most relevance to and most use in compilers. So for instance, lexers use regular languages, but parsers use context-free languages. And parsing is one of the big problems, probably the biggest problem in compilers. So restrictions placed on a regular grammar were just that we had any number of terminals followed by a single non-terminal, or a single non-terminal followed by any number of terminals. So we're going to relax those restrictions and say that we can now have non-terminals, any number of non-terminals appearing kind of anywhere in the right-hand side of a production. So any number of terminals and non-terminals in any order. But we're going to find that there are some issues with some of the grammars that we could create from this. And we saw, here was an example of a context-free grammar. We looked at this grammar, we found that we could produce WWR with this grammar, another language that we proved to be not regular in the last set of slides. And this grammar was able to be modeled that way. We found that it was not possible to do this with a regular grammar or with a state machine. And that's because we're adding in the middle rather than trying to add from either side. So we ended the class before last, I think, looking at this. We came up with a couple of different ways to produce this grammar. There was a nice one by Patrick that was slightly more intuitive than this, but this also works. The idea is we kind of have an if statement that says we either need to go into some set of rules that can generate an equal number of A's and B's and some A's without some B's, or we need to generate an equal number of A's and B's and a rule for more B's than A's. Or only B's rather than, or only A's. These last two rules only generate A's in the front half of the string, and the last one only generates B's in the last half of the string, which is placed by this fact that the B is after what generates the A's and B's, and the A is before. So that's what causes these A's to be in the first part of the string and these B's to be in the second part of the string. The second part was wrong, you can ignore it. Then we looked at this grammar and said, what language is accepted by this? And we found that it looked like it was an equal number of A's and B's. But upon further inspection, we found that it had to start with an A. It had to end with a B. So there were some extra restrictions on just the equal numbers of A's and B's. And that's that if there were at any point in the string, there could only be more A's than B's, or an equal number of A's and B's. There could never be more B's than A's at any place in the string, which was curious. So we found some of the strings from this looked something like this. These were some strings that could be produced. And then I asked what this might map to in programming language syntax. And the answer to that was mathematical parentheses. If we replace A's with a left parentheses and B's with a right parentheses, then we end up being able to model parentheses with this fairly simple grammar. We last went into the concept of leftmost and rightmost derivations. We kind of defined this, but didn't really do much with it. We looked at the concept of grammar ambiguity, which is something that becomes a major problem in grammar design. So we defined grammar ambiguity in terms of whether we can have a string that can be produced with two different paths through the grammar. If we do this, then, so here was the example that we used. Here is a grammar, and we found that we could generate the string AAB in at least two different ways. We discovered that there were actually significantly more than two different ways that we could produce this string in terms of the order of the productions that we applied. It seems like this might be a good thing because options, but if we look back on imagining that this is something that models programming language syntax, now we would have different ways to produce the same instruction or ways to interpret the same instruction differently, which turns out to be horrible. We don't want to have multiple different ways we can interpret an instruction. We don't want multiple different ways to generate the same instruction from that. So it's not good if we have that. So eliminating ambiguity, if we can determine the order in which the non-terminals are replaced. This means that we're either going to move from left to right. And you can see that the first one here is a leftmost derivation because we are always replacing the leftmost non-terminal. So here we replaced the S, then we replaced the A, then we replaced the A, then we replaced the B, then we replaced the B, and got this. So it's always the leftmost non-terminal. Here it was always the rightmost non-terminal. We replaced the B, we replaced the B, we replaced the B, we replaced the A, and got there. So kind of from the right side. Now there's only one way to go through this grammar if you don't allow replacing arbitrary non-terminals. So the leftmost non-terminal, always leftmost derivation, rightmost non-terminal, always rightmost derivation. And if you have ambiguous grammar, statements can be interpreted differently, which is scary. In a programming language, whenever you write something, you mean exactly one piece of logic. There can be no ambiguity in what you mean when you do this, which would mean that different compilers could interpret the same statement in different ways. We don't like that. All right, so here's where we're at new content for everyone. That's kind of the summary of what we covered last time. So we're going to look at another grammar. Here it is. And go ahead and provide a leftmost and rightmost derivation of the string ABBBB. So we know we have to start with the start non-terminal. Then we must replace the A if we're doing the leftmost, the capital A. Then we must replace the leftmost non-terminal that is left. Etc. Very digital sounding professor next door. Again, there should be no ambiguity in this. You should have no decision making to do. There should always be a right answer about whenever you have options about how to apply them. Like, for instance, the B can be an A or a lambda. It should be obvious which one to apply. And on the rightmost derivation still, that's fine. I'll let you compare to my leftmost derivation. People got. And the rightmost derivation. So what did we think about this process? Were there difficulties that people ran into? If so, what were they and what happened?
So
Yeah,
while still doing the derivations in the same order, for example, at most, when you get to the point where there are two capital B's, uh, why couldn't you do the derivation that goes B to null and then
the last
wait
one,
until the last B to add more ones?
So we
Because-
will see basically that this does lead to ambiguity.
Okay.
And this is why having an ambiguous grammar is bad.
Mhm.
So this is actually ambiguous. And it's that way on purpose, so that you do discover exactly that. So we'll actually eventually find an algorithm for going through a leftmost or rightmost derivation. And if the grammar is not ambiguous, then there is only one path through that to generate the string. But if the grammar is ambiguous, then there may be multiple paths that produce the same thing. But we always know exactly what the next terminal is that we're trying to derive. If we're doing a leftmost derivation, when we end up with the leftmost next terminal, we know the sequence of rules to apply, and we can do an intelligent search through that production space to try to generate the leftmost terminal being the terminal that we're looking for. And if the grammar is not ambiguous, then there's only one way to do that. There's only one sequence of productions that will produce exactly that sequence that you're looking for. So to help with this, it's useful to actually draw out a parse tree. And I've tried to model this a little bit in some of the examples that I've been using up to this point in the class. So you can think of a derivation in terms of a tree structure. We start with a node representing a non-terminal, and then we will have children of that node being whatever sequence of terminals and non-terminals that are produced. So if this were the tree structure, let's just first say that, of course, each non-terminal node gets further expanded into something. How would you, given this tree structure, output the string that the derivation represents? If that question makes sense. If we drew out the leftmost derivation from the past slide as a tree like this, how would we go get the A, B, 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 B out of it? With only the internal representation of that tree structure.
Would it basically be a depth first?
That's exactly right. Yeah, you want a depth first search through the tree because the first terminal is going to appear left, 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 left down that at the first leaf. Since we know that all leaves are terminals, how do we get a left to right leaf output via a depth first search? Yeah. Questions on anything about the parse tree structure, how to represent it? So you'll just start with the root node being the capital S, the start non-terminal. And from there, you will do some kind of expansion of all non-terminals until a depth first search of the leaves reveals or prints the string that is what you were trying to derive from that grammar. If that makes sense, let's go through an example. We're going to have this familiar grammar. Go ahead and construct a parse tree for that string. follow your leftmost or rightmost derivation example to help you construct that parse tree. That can certainly help as you see the order of what you did as you came up with that derivation. That will be kind of either a left to right depth first search or right to left depth first search through the tree that you generate. So here's what a tree could look like. We see that the S expands into A capital A B, that A expands into B capital B B, that B expands into the empty string, etc. And if we do a depth first search through this tree, we see that we get A, B, 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 which is the string that we wanted to derive. And if we did a rightmost derivation, we would be doing a right to left depth first search as we created it. If we did that, we'd be reading the string from right to left if we did that kind of depth first search. Did anyone derive a different parse tree from this one? Could there exist a different parse tree than this one? Intriguing questions. So what's nice about parse trees is it shows the productions, doesn't show the order of application. So that means that a single parse tree can be used for a leftmost or a rightmost derivation. This isn't a leftmost parse tree or a rightmost parse tree. You can iterate either left to right depth first or right to left depth first as we do a leftmost or rightmost derivation. So parse trees are super useful for this because they help you to determine whether a grammar is ambiguous. If there exist multiple different parse trees, then the grammar is ambiguous. All right, we're gonna start to talk about the membership question, which is a very important question for grammars. We have a query string. Is it in the language of the grammar? Right, we ask, is AB, BB in the language of the grammar on the prior slide? So, thoughts to the class. How could we answer the question?
Technically brute force it.
Yeah,
I have
Try
ways to
everything?
actually get it
what's the complexity of that?
very big.
Yes. That is the answer, very big. So yes, brute forcing by applying every possible production at every possible stage. So that's basically this idea. Generate all possible leftmost derivations from the grammar, see if one of the derivations matches the query. So to do this, you would look at all possible derivations from the start non-terminal within a single step and see if any of them match the query. So if we're trying to generate the string A, B, 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 we would look for one step from the start non-terminal and say, do any of these immediately generate the terminal A within a single step? But that's not necessarily guaranteed to be true. There may be a non-terminal on the left side of every one of those, in which case we'd have to recursively look at every possible sequence of productions that all of those could produce to see if any of those generate the leftmost terminal being an A. But there's no guarantee that any of those have terminals. And there's no guarantee that if you find one that is a leftmost A, that it's the only one. Maybe there are multiple paths through this that lead to that. So step 2 is applying all possible applicable productions to the leftmost variable of each resulting derivation from this. Great. When we do that, we're going to kind of cut off this tree that we're generating of possible sequences of productions, rejecting any derivations that can't produce the query. So if one of them produced the leftmost terminal of a B when we're looking for an A, that can't possibly be a path through this grammar, right? It's producing the wrong string. It doesn't matter what we do from here, we've already made a mistake in generating this. So we cut off those branches of the tree and only continue down paths that could be producing a string. So then we repeat these steps for the next resulting leftmost derivation as we're resolving leftmost, 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 generating only the strings that match what we are looking for. The idea is that if this string is in the language, then there exists a leftmost derivation in some finite number of steps. So this will eventually reveal some path to generate that string if it exists. If we look at everything that we can do in one step, regardless, there are a finite number of productions, so we can only do a finite amount in one step. So note that this is more of a breadth first search than a depth first search, because a depth first search may not terminate. The leftmost non-terminal of some path of an A may be a B, then an A, then a B, then an A, then a B, then an A, then a B. There's a way to generate an infinitely long string that would never terminate. So we don't want to apply a depth first methodology here because that would potentially create an infinite loop generating an infinitely long string. We would never be able to answer the question whether the string is in the language. But if we do more of a breadth first search idea, then we look at everything we can do in a single step, and then everything we can do in 2 steps, and then everything we can do in 3 steps, everything we can do in 4 steps, as we resolve those non-terminals in ways that generate only the kinds of strings that lead to the, so far, the leftmost part of the string matching the query string. If that makes sense. I'm going to label this brute force parsing, because as you can imagine, this is disgusting in actual practice. It will get you an answer if an answer exists. You just might be dead before you know. Humanity might not exist by the time that you know, given an arbitrarily long grammar and an arbitrarily long search string. So, issues. It's tedious and very inefficient. May never terminate for strings that are not in the grammar's language. That's a huge issue here. If the string is not in the language and the grammar can generate an arbitrary sequence of non-terminals because the language is infinite, this can answer the question, yes, the string is in the language, but may not be able to answer the question, no, it is not in the language. How would you know at any point in time that this grammar is never going to generate that language? How would you know whether to terminate or not? That's a really hard question to answer. And in fact, it's not a question that you could write a program to answer. We'll discuss this later on in the class as part of the what can we do and what can't we do with programs. This is one such thing we can't do. Given this algorithm here, we cannot write a program that will tell us the answer, no, this string is not in this language, given a particular kind of grammar that can generate an infinitely long string. So of course, the issues come from production qualities that can reduce the length of a derivation or keep it the same via one step. So we don't actually generate new characters. We just go from non-terminal to non-terminal to non-terminal to non-terminal to non-terminal. We don't know at any point if we're ever going to reach a point where we can generate the character that we're looking for. So the solution to this is that we need to disallow certain kinds of grammar productions. If you do this, then we can actually answer no. If we have non-terminal directly to lambda. That is the first very bad form in a context-free grammar. The next one, non-terminal, arrow, non-terminal. This is also bad. Any thoughts about why either of these prevents us from being able to answer this question?
Non-terminal can loop without changing the habit string.
Yeah, non-terminal and a non-terminal, you can always have, A arrow B, B arrow A, creating a loop. As soon as you do that, and it may not be that obvious, it may be 17 steps of derivations lead you right back to where you started without revealing some terminal. And if you do that, then that's a problem. Great. What about the non-terminal to lambda? Basically, if we disallow these two things, what does that state about having a non-terminal in your grammar? You guarantee that every single non-terminal leads to one or more terminals, which allows you in a finite number of steps to determine whether a string is in the language or not, because eventually you can chop that off saying there's no way that this grammar can produce a string that is as short or shorter than the query string. Every string that it generates would have to be longer than that. So ABBBB was 5 characters. If you'd already generated 5 terminals and all that was left were non-terminals, you know that those non-terminals can only produce terminals from there. They can't produce nothing and I'll go away and have the query string. They can't produce additional non-terminals to loop forever. So they must eventually, in some finite sequence of productions, become terminals. Which tells us that that branch can't produce the query string. So do note that neither of these productions, or restrictions on languages, sorry, affect the power of a context-free grammar. There's always an equivalent grammar. If you were to write a rule of this form, you can write one or more rules that would make an equivalent grammar that don't adhere to either of these production form types. If we do this, then we can actually answer the question no. Whether a query string cannot be generated by a particular grammar. And we know that the total number of leftmost derivations replacing a non-terminal with some production must be less than or equal to twice the length of the string. So if the query string is 5 characters, within 10 leftmost derivations, we must have terminated. The depth must be 10 or less. And now we could even do a depth first search if we wanted to. We don't have to do a breadth first search. We could do a depth first search that terminates at depth 10. And that would allow us options as to how to determine whether a string is in the language of a context-free grammar. Thoughts on this? Any other thoughts? Does this make sense? So of course, we said it's tediously inefficient, but what is the actual computational complexity of this brute force parsing? we can break this down into steps. So the first step is to think about what are we doing with each leftmost derivation? What is the worst case of what a leftmost derivation can generate? And in the worst case, a leftmost derivation can generate a number of leaves in that tree equal to the number of productions in the grammar. Each one of those is a leftmost derivation, which could reasonably have a branching factor of the size of the number of productions in the grammar. And we only have to go to depth 10 if the string is length 5, but if the string represents every character or every token in a programming language, what is the longest program that you've written in terms of the number of tokens or the number of instructions? You can imagine how the branching factor for this, given the size of a grammar of a programming language, where every single node becomes however many productions that you could take from there, generating thousands upon thousands of instructions, you can see how this is not feasible. It works for toy examples, like what we are doing right now with the alphabet AB and strings that rhyme with baba and bab and ab, ab. But when we get into actual programming language syntax, this becomes horribly infeasible. So at most 2 times the length of the string, repetitions of the process. So we end up with the number of productions in the grammar to the 2 times the length of the string, number of derivations parsed, which of course grows exponentially with respect to the length of the string, which means as you get large strings, this becomes computationally infeasible, which is gross. So we need something that is more efficient. Any idea what the optimal complexity is for this? Just you had to take a stab and a guess. With all of humanity's brilliance put together, the best we have ever done on this problem is what? In terms of a computational complexity. Anyone want to throw out a guess?
Is there a binary search?
Binary search would be amazing. That's logarithmic, right? We're nowhere near that close. Would love that. That'd be amazing. The answer is cubic. We can get down to the length of the string cubed. Is there anyone have a guess at the algorithmic technique that might be used to reduce this exponential complexity, this kind of algorithm, down into something that is cubic? What in general, what generic programmatic techniques do we usually have for reducing an exponential complexity brute force problem into something that is polynomial? Dynamic programming. It's always, a lot of the time, it's dynamic programming. So if you've heard of this in algorithms classes and played around with, I don't know, what does Corman use? Rod cutting, matrix chain multiplication. Does anyone remember, or did you go through any of those kinds of examples? Because I know the algorithms course here uses the Corman book for that.
That's one of the first classes you take, so that was actually good.
Right. A long time ago. Luckily, you'll be getting some practice with this in the big course project, because this is exactly what you're going to be implementing, is this cubic algorithm. So we're going to return to this as we discuss the parsing problem, and eventually you will be implementing this algorithm, and it's incredibly useful. And it generalizes to all sorts of other problems, not in compilers. I don't know exactly the reason that all of you are taking this course. It could just be that it's a requirement. It could be that you thought it was interesting. So I want a project that you can add to your code portfolio that shows, that demonstrates understanding and mastery of a concept that applies broadly beyond compilers. That shows I understand how to write a dynamic programming algorithm. I did one myself to solve this problem, and here you go. Useful as you go apply for jobs in this field. So we can get this cubic time down to linear only in very special cases, but those special cases are important to compilers. This is what we'll probably come back to as we have time, but we will be returning to this problem in not too long because I want to give you a reasonable amount of time to do this project. Questions on brute force parsing, why it's bad? We'll study this in a lot more detail soon-ish. There is another interesting and useful kind of grammar called a simple grammar that ends up being a restriction on context-free grammars. So a simple grammar is a context-free grammar if every single production follows what looks like a similar form to the regular grammar. Instead of a single non-terminal followed by an arbitrary number of terminals, we get the exact opposite. A single terminal followed by 0 or more non-terminals, as well as any pair of non-terminal to terminal appears at most once in the grammar. Do each of these rules make sense? Here are some examples. Your task, tell me if they are simple or not simple. Does this grammar adhere to both of those rules? No. Which one does it violate? So pair of non-terminal to terminal appears at most once in the grammar. Which two productions violate this? So non-terminal to terminal. This says the first production is S arrow A something. And the second one is S arrow B something. So those are distinct in the non-terminal arrow terminal portion of that. We don't care about the non-terminals that follow afterwards. It's just looking at the non-terminal arrow terminal aspect of it. So we have an S to A production. We have an S to B production.
So we don't want to care about the other terminals.
Correct. That's a very good clarification, which is why I use this as an example, is to make that clarification clear. So with that in mind, simple grammar, not simple grammar? It is a simple grammar. How about this grammar? This one is no. Yeah. Why?
Because of AS and ASS.
Yeah, so we have an S arrow A production and another S arrow A production. It doesn't matter what non-terminals follow that. Now we have a way to branch and create. You can imagine that if we are trying to parse this and determine which sequence of productions to apply to produce a particular string. We don't want there to be a branching factor. If it's a simple grammar, then there should only be one appropriate, given that we're right here, if we want the next symbol in our string to be an A, there's only one production we can apply here, that one. Here, there are multiple options, which creates a branching factor, which is not simple. So think of simple as a branching factor of 1. There's always a right answer with regards to which production should you apply, given that the next character you want in your string is a particular term.
Basically make sure that if you want a string, you can only go one path and it has to be on the one here, no matter what you do.
Yep. So features of programming languages can be described by simple grammars. If it's possible to describe them by a simple grammar, we want to do so, because you can see how this is a now linear search. There's no branching factor. So depending on the length of the string, we only have to apply that many productions, given that we're getting at least the next terminal, and there's only one possible path through the grammar. So those simple cases that can be linear utilize simple grammars. Questions on simple grammars? Just kind of a very quick aside. We're not going to go into too much detail about simple grammars unless, of course, we have time at the very end of the course to kind of come back to the applications of all of these. We're going to do that in some cases, but we'll just see how much time we have and do application after application after application with all that time. All right, we need to talk about grammar ambiguity. We've talked a bit about it, but we're gonna go into a little bit more detail because it's a very important problem. So we know grammar is ambiguous if there exists a string in the language that is defined by that grammar that can have multiple different parse trees constructed that derive that string. Hinted at this before, but now we're going to officially define it as for a string, multiple parse trees can be constructed from that grammar that derive that string. And we're going to come back to examples of this tomorrow. Any questions on anything from today? Kind of just very quickly going through a bunch of topics, but they all come together by the end of the class. All right, thanks everyone. Thank you. See you tomorrow. Let me know if you have any questions about homework. If you didn't get a chance to see your quiz and want to see your quiz exam, let me know and I'd be happy to show it to you.
All right, were you able to talk to them about it?
About, sorry, what was it? Yeah, I have not had a chance to talk to Hunter. He was out yesterday, so I'm gonna go talk to him right now.
Here's them sending me the email.
Yeah. Sounds good, will do.